Assalamu alaikum dear students, welcome to the online lecture on MATLAB simulation of control systems. Today we are going to discuss this research paper that discusses the stability analysis for switched positive linear systems under state dependent switching. This paper is published in the International Journal of Control Automation and Systems in 2017. As usual, we are not going to go into the details of this paper. Rather, we are just going to look into the stability analysis method that is discussed in the paper, and we shall be looking into the MATLAB simulation of switched positive linear systems. This paper basically discusses the systems of the type x dot equal ax, where A is supposed to be a Metzler matrix. A Metzler matrix is a matrix for which all the off-diagonal terms are non-zero. A Metzler matrix is a matrix for which all the off-diagonal terms are non-negative. So the off-diagonal terms can be either positive or zero, but cannot be negative. The linear delayed system is also discussed in this paper, for which the system is of the type x dot equal ax plus b times x of t minus h, and x of t minus h is a delayed value of the state variable, where h is the value of the delay, and B matrix is also supposed to be greater than or equal to 0. So this tilted greater than or equal to sign means that all the elements of B are non-negative. So for a matrix, this type of sign means that element wise every element is greater than or equal to 0. Then there is this first result, which is taken from these references, which basically states that x dot equal ax is exponentially stable if and only if there exists a vector v greater than 0 in Rn such that A transpose v is less than 0. So vector v greater than 0 here means that every element of this vector is greater than 0, and here again this A transpose v is another vector which is strictly less than 0. This can be proved with some sort of a Lyapunov function discussed here. Vx is equal to x transpose v, which we are not going into. Then there is this result that x transpose w not greater than equal to 0 whenever x transpose w1 greater than equal to 0 and there exist. So these are like a few conditions for the delayed state variable cases, which are going to be later on matured into the conditions derived in this paper for the stability of switched positive linear system with delay. And then there is section number 3, switched linear positive system composed of LTI subsystems, x dot equal a times xt, where x is the element of Rn, sigma is the element of Rn with only positive numbers, and m is 1 2 3 or up to so on. M is the switching signal, which is state dependent. So that's the speciality of this the systems discussed in this paper, that the switching signal is dependent upon the state variable state vector values. AI again is the Metzler matrix. So here basically what they discuss is that when you can switch the system from one dynamic to the other dynamic. So x dot equal a1x can be switched to x dot equal a2x depending upon the conditions that are dependent upon the state variables. Then we have some more results, and the most important result, there are two most important results in this paper. The first one is the theorem 3, which states that the switch positive linear system is exponentially stable if there exists a vector v and vectors wi. belong to Rn for positive scalars Ci such that the following conditions are satisfied. First of all, the v vector, every element of v vector must be greater than 0, and then ai transpose v plus ci times wi. This is a vector in Rn. Every element of this vector should be less than 0 for all m. So m is the number of models in the system. So for example, for m is equal to 2, you have x dot equal a1x and x dot equal a2x, and you can switch between the two models dependent upon some condition, that is state, that is a function of state variable. Then there is the second most important result in this paper is this theorem 5, which states that for ij belong to m, switched positive linear system is exponentially stable if there exist vector vi, wi and the scalars ci and ai such that the following conditions hold: vi minus ai times wi greater than 0, a transpose vi plus ci wi less than 0, and so on. So these are the three conditions for exponential stability of switched positive linear systems. And then comes the main point of interest for us, which are the numerical examples that we are going to see how to simulate on MATLAB. So we have a switched positive linear system where x dot equal a1x if x is such that x transpose w1 is greater than equal to 0. Otherwise we have x dot equal a2x if x is such that x transpose w2 is greater than equal to 0. So where w1 and w2 are given in the paper, and also the values of a1 and a2 matrices are given, and then they say that you can use theorem 3 for this system, and you can solve the linear programming for this. You can solve this. This is basically a linear matrix inequality, the equation 5. You can solve this and you can get well, there are many possible solutions for equation 5 in this case, but one of the possible solution is that v is equal to this with the value 1.55 and 2.24, and c1 is equal to 8.2 and c2 is equal to 7.7. I will briefly show you how you can solve this inequality in this video as well, and then I will show you how you can get these results from this example. So let me just open this MATLAB file. So here is the file. You have to first of all, as usual, in order to solve the differential equation, this is the switched differential equation. So there will be the dynamic, these are the values of the a1 and a2 matrices given in the paper, and these are the values of w1 and w2 vectors given in the paper. And then you have the condition that x transpose w1, if that is greater than equal to 0, then you use x dot equal a1x. Otherwise you will use, otherwise if x transpose w2 is greater than equal to 0, then you use x dot equal a2x. And this condition I have just added just to be sure that there is no other condition than these two. So if there is another possibility, then I will this will display the message exception, and in that case I have just randomly selected x dot equal a1x. And if I run this system, so I need another file to call this system. So this is example 1, and I will just run it for let me see, if I go here, I just need to run it for 5 seconds, and I will use the initial conditions 8 and 2 as used in the paper. So 8 and 2, and then I will run this file, and then these are the results will be here soon. Okay, so here are the results. Let me just close it and run the file again. So if you run the file, so here are the results, and this is the result given in the paper. So if you compare the results that we have obtained using our simulation and the paper, you can see here the results that we have obtained are a little bit smoother than the ones presented here in the paper. That depends upon what kind of a solver they have used. We have used the ODE 45 solver for the equations, the switched linear systems. If I zoom into the state variable trajectory, we can already see that there is some jittering, some sort of chattering in the this state trajectories, but not as much as this one. But the overall trajectory is sort of common, that you start from 8 and you straight away decay, and the other state variable starts from 2, goes all the way up to almost 3. Here it goes a little bit above 3 and then goes down, and here in our case it goes up to 3 and goes down. So there's a little bit of a difference, but I think that's okay. Then the next example is the same as the example 1, but only the A1 and A2 matrices are different. So in order to, this was the code for example 1, and this is the code for example 2, and the only difference between the code for example 1 and the code for example 2 is the value of A1 and A2 matrices. And now we can run this. Here we use now example 2 and run this for say 200 seconds, and the initial condition, we use the same initial conditions that have been used by the authors in the paper. And we run this file. It will take some time, and we'll see the results soon. But these are the two examples. So these are the results, and you can see here that these are very similar results, except that we have a little bit lesser magnitude of chattering in the state trajectory than the amount of chattering here. Also another difference is that I have run it for only 200 seconds, and if this plot is also in seconds, then this is taking much longer time. Maybe this unit of this t is not seconds, I am not sure, but okay. So if I plot this, if I magnify this, you can see there is a lot of chattering here because these matrices here are a little bit different than these one. So the system still is exponentially stable, the switched linear system. But notice that the individual system x dot equal a1x and x dot equal a2x, in both the examples the individual systems are not stable. You can find the eigenvalues of this A1 matrix and A2 matrix and verify that these systems are actually not stable. But if you use them as like a switched system, it becomes exponentially stable. It's very interesting. And also then there is so the case of switched linear systems with delay. So in this case you have x dot equal ax plus b times the delayed version of x, where the amount of delay is given by this h. And there are some examples where theorem 5 has been used for improving the stability. This is example 3, which is the first example of the system with delay. So if you want to so since this system has a delay, you cannot use ODE to solve this system. You have to use a delay differential equation. So delayed so here this is the example where we solve the switched linear system with ODE. And ODE, when you write the function for ODE, it has only two parameters, time and the state vector. But when you are trying to solve the delay differential equation, the corresponding function will have three parameters: the time, the state vector, and the delay amount. So here h is the delay, and in this paper the h is 0.05. And when we so A and B matrices are given here, A1 A2 B1 B2. We use the same A1 A2 B1 B2 here in our code. So these matrices are used here, A1 A2 B1 and B2, and then W1 and W2 are the same, and the switching condition are also the same. If x transpose W1 is greater than equal to 0, then x dot equal A1x plus B1 times. So this is the way of writing x of t minus h. You just write B1 times h, so this h, and then x dot equal a2x plus b2 times x of t minus h. So here h is basically acting as x of t minus h. This is how the delay differential equations work in MATLAB. And then you can basically call this using a script file. So script file corresponding to that is here. So this is the script file, and you can first run the example 1. So here we have given here that we have told we have used the function DDE23. DDE stands for delay differential equation, and if you want to find more details about this function, built-in function of MATLAB, you can write help DDE23 in the command window, or you can write doc DDE23 like this. So you can write either help DDE23 and press enter. I'm not going to press enter here. Doc DDE23 and press enter to get more information about this function. So we in DDE23 we tell MATLAB which file we are going to use. So here we are going to use this function file that we have written, and we are going to tell that how much delay is there in the system. So this is the value of h, 0.05. Then we are going to tell the history or initial conditions, 3 and 12. These are the initial conditions. So notice here that initial condition vector is given in the column vector form here, and then there is the time span 0 to 8 seconds. So these are the and then once you have the solution of the delay differential equation, solution dot x will be the time and solution dot y will be the state vector. So you can run this file and get the results. So here you can see here the results are here. So these are the results of the delay differential equation, and we can compare them with the results in the paper. So these are the results in the paper. So again you can see here that the results in the paper, the state value starts from 12 and goes all the way down, and here is the same behavior. The second state starts off from 3 and goes all the way up to maybe 5 point something, and here again it goes like a little bit less than 6 and goes down. So behavior is very similar in both cases. So if you again zoom that in, you see the chattering or the oscillatory behavior in the state trajectories. Anyways, so this is the example 1, and similarly you can write the code for example. So only difference in example 2 is the value of the A1 and A2 matrices. The whole code is the same. In this case this is the example 3, which is the first example of delay differential equation, and this is example 2. The only difference here and the other example is the value of A1 and A2. And if you use, instead of this command Control R, if you use this command and run, it will take a lot of time because we are running it for about 100 seconds, but eventually the results will be here. So finally, after quite a bit of a wait, the results are here. So these are the results of delay differential equation for the second example. You can see that from the 18 value the state goes down as it does here, and the other state is going up to the value of about 9 and then going down. Here the state value again is, starting from 4. The blue state is going, sort of like up and going down. And again we can zoom in and see the detailed behavior of the state variables, and that will give you some idea of the effect of switching on the trajectory of state variables. But it is incredible that the overall switched linear system is exponentially stable. Okay, so that is it. Oh, one more thing. If you want to solve this if you want to find out whether your own switched linear system satisfy these conditions or not, you will have to use linear matrix inequality. Although this paper suggests using of linear programming to solve this equation 5 and equation 9, but I have found that linear matrix inequality, which is sort of let me show you. There is a function FEASB. So let me show you this. Yeah, so this is the linear matrix inequality program that I have written for. So first of all, you have to set LMIs, and this program is just for this equation 5. So I have broken down V into V1 and V2, two scalar variables, and C into C1 and C2 are already scalar. So I have also broken down this A1 matrix in the example to be A11, A12, A21 and A22. So if you go to the this A1 matrix, so A11 is minus 8.5, A12 is 1, A21 is 0.2 and A22 is 3. You can just take a screenshot of this code and rewrite it in your own way, and then you will see how it works. And if you want to see the details of how this LMI term, how you define the LMI term and how you define the LMIs, and this is the main function, built-in function of MATLAB, FEASP, which solves the LMIs and give you the solution in the XFEAS. So XFEAS will contain the solution, which will contain the value of V1, V2, C1 and C2, and then you can check whether X1 A1 transpose V plus C1 into W1 is all negative or not, and you can also check this. And you can also check whether V1 and V2 are both positive or not. Let me show you. If I bring in the MATLAB, so if I run this file, so well, there is a problem on line 23 where I have used V, so I have to define V is equal to V1, V2, or maybe I can just have this to be V1, and then I can define another LMI term, so V2, because we want both v1 and v2 to be, so this will be LMI number 6, and this will be the right hand side of LMI number 6, and we save it and run it. So this is the solution of LMI. You can see here this is check 1 and check 2. So check 1 check 1 is basically that A1 transpose x feasible, first two values of x feasible is v1 and v2. So because LMI variable, so here we have defined 4 LMI variables, v1, v2, c1, c2. So this one shows that my variable will be a symmetrical matrix, and this one shows that it is a matrix of size 1 cross 1, and this one is for I've forgotten what this one is for, but you can just write help LMI VAR in the in here. If you type something like help LMI VAR, then you can see what all of these parameters are about and how they are set. And then well, you can set up these LMIs, and then the solution x fees. So there you have it. This is the value of v1 and v2, and this is the value of c1, this is the value of c2. These values are different from the values of values given in the research paper, but that's okay, because there is not a single solution for this linear matrix inequality problem. There are multiple solutions, and we have found a feasible solution using LMI, and the authors have found one feasible solution using linear programming. So you can also use linear programming if you like linear programming more than the LMI, but if you don't have any experience in linear programming or LMIs, then I personally prefer using LMI for this particular problem rather than the linear programming, because that's actually for optimization. We don't need an optimal solution here, we only need a feasible solution. Okay, so that is it for this video. Once again, as a recap, this is the example of switched positive linear system, and this is the example of let me show the example of switched positive linear system with delay. So this is the example of switched positive linear system with delay. To write a function for delay differential equation, there is an additional parameter, delay parameter, and then similarly when you're calling this using DDE function, then you have to provide the parameters, the function file name, the value of the delay. By the way, you can use more than one delay values in solving the delay differential equation. The history of the state variables, and which in our case it is just the initial conditions, and the time span for which you want to solve, and then when you have the solution, then solution.x will be time and solution.y will be the state variables. And finally the solving of this LMI. So this is the LMI code that I have used. So LMI term, you can see you can write help LMI term to find out how I set these different parameters. So this first one is the number of LMI, and if it is negative, then it means that this is the right hand side of LMI. If it is positive, then it is left hand side of LMI. Here are these variables of LMI, and this are the multiplication matrices or vectors given here. Then you gather all the LMIs in the structure LMIs and give it to the function FEASP, which give you the minimum time and the value of the LMI variables, and then you can see whether your switched positive linear system satisfy the linear matrix inequality conditions or not. So that is really it. I hope that this video will help you in starting your research on stability analysis of for switched positive linear systems. Thank you.